Since the early 1990s, astronomers have known that extrasolar planets, or exoplanets, orbit stars light years beyond our own solar system. Because most exoplanets are too far away to be directly imaged, characteristics such as size, composition, and atmospheric makeup must be determined through a variety of indirect methods. For instance, when an exoplanet passes in front of its star or transits, it blocks a fraction of the star's light and causes a dip in brightness. Large planets block more light, so the size of the dip can be used to determine the size of the planet. By observing an exoplanet's gravitational pull on its star, astronomers can also determine the planet's mass and thus calculate its density to see if it is composed of rock like Earth or gas like Saturn. But to fully understand an exoplanet, astronomers must study its atmosphere, and the information that they need is encoded during a transit. As the planet crosses its star, its atmosphere absorbs certain wavelengths of light or colors, while allowing other wavelengths to pass through. Because each molecule absorbs distinct wavelengths, astronomers spread the star's light into its spectrum of colors to see which wavelengths have been absorbed. The dark absorption bands act as molecular fingerprints, revealing the atmosphere's chemical makeup. Knowing the depth and density of the atmosphere is also important. To figure this out, astronomers observe the transit at many different wavelengths. At wavelengths where more absorption occurs, the planet will appear larger, with the change in size indicating how deeply the atmosphere extends, and its density at different altitudes. Measuring the depth of absorption at each wavelength gives astronomers the planet's transit depth curve, which allows them to model the composition, height, and density of the atmosphere, providing a detailed picture of the planet. Recent studies suggest that exoplanets and their atmospheres come in a wide variety. At one extreme are hot Jupiters like WASP 19b, a boiling gas giant that orbits its star far closer than Mercury orbits our Sun. Visitors who could survive the heat might complain about the air quality. By contrast, planet Gliese 1214b is a comparatively inviting water world. Its nearly flat transit depth curve hints at a shallow atmosphere of pure steam, enveloping an ocean thousands of kilometers deep with an interior of hot ice, water solidified by extreme pressure rather than cold. As detection methods improve, astronomers will search the atmospheres of Earth-sized planets for signs of life such as water vapor, oxygen, and methane, taking us one step closer to finding a world like our own, all thanks to some flickering starlight.